In this module, we are just trying to elaborate the concept of conservation of momentum. And in our case, we are considering and we are assuming the conservation of linear momentum. Okay, so conservation of linear momentum. So think about it. If suppose two or a more body, if two or more than two bodies are acting to each other in an isolated system. When I am saying acting to each other, that means what? They are some of the bodies giving force to the other, and some of them accept the force. This is the interaction is going on. Interaction, or the what should I say? Interchanging of force, right? Giving and receiving of the forces is going on in a system, right? By the two or more than two bodies, right? The conservation of momentum says the momentum remains constant. The momentum remains constant if no external force is applied. So that means what we have? We have that the momentum can neither be created nor it can be destroyed. So I am repeating again the thing, that is what? If two or more than two bodies are acting or interacting to each other in an isolated system, right? If no external force is applied, the total momentum of that system, right? The total momentum of that system remains constant. So now let's take an example. That is, there is a two particle. The first particle having mass m1 and the velocity u1, and the second particle having mass m2 and the velocity u2. Now think about it. If u1 is greater than u2, and if both the particles are moving in a same direction or in the same way, right? Or in the same way or the same direction, so that means the collision must be happened, because the first particle, the velocity of the first particle is higher than the second particle, because u1 is greater than u2. That means collision will be happened, right? So if collision will happen like this, think about it. Velocity will not constant like in the previous u1 and u2. The mass of both the bodies must be constant. There is m1 and m2, because mass cannot be changed, right? If you apply the force to any kind of body, the mass cannot be changed, right? So, but the velocity must be changed. So now after this collision, the velocity will be, for the first particle the velocity is v1, and the second particle the velocity is v2, right? Now think about it. Before the collision, the total momentum of that system, or the total momentum of two bodies is what? Before the collision, the total momentum of these two bodies, if we add this momentum, the momentum of the first particle was what? m1 into u1, and the momentum of the second particle was m2 into u2. So that means if we add this to m1 u1 plus m2 u2, this is the total momentum of the two bodies or the two particles before the collision, right? So, and after the collision, the total momentum will be, think about it, m1 v1 plus m2 v2, because after the collision, the momentum of the first particle will be m1 v1, and the second one is for m2 v2. So if we add this to m1 v1 plus m2 v2, these are the what? The total momentum of two bodies, or you can say the total isolated system is what? m1 v1 plus m2 v2, the total momentum. Before the collision it was m1 u1 plus m2 u2. After the collision it will be m1 v1 plus m2 v2. Now think about it. If we apply, or if we follow the law of conservation of linear momentum here, that means the total momentum of any system or of any isolated system is always remains constant if no external force is applied. So here we are not applying any kind of external force, right? Because these two bodies are just moving with their velocity. No external force is given in that system or for both the particle. So that means we can say before the collision, the total momentum must be equal with the momentum after collision, right? So that means before the collision, the momentum was what? m1u1 plus m2u2, and after the collision, that is what? m1v1 plus m2v2. These two equations must be equal according to the law of conservation of momentum, and you can say linear momentum. And we have given an example of in one-dimensional case, right? In class 11 or in the higher, you will have the three-dimensional example of to prove the law of conservation of linear momentum. And now think of, there are two cars, the same phenomena, two cars, m1, m2, and before the accident or before the collision, the velocity was u1, u2, right? And now if u1 is higher than, or if u1 is higher, or if the speed of the fast car is higher than the second one, then the accident must be happened. If they are both are going in the same way or the same path, right? Accident must be happened. But after the accident, the velocity will be v1, v2, because the velocity must be changed. Their mass of the car cannot be changed, right? But the velocity will be changed. So if the velocity will be changed, the thing is, but the total momentum remains constant. And here is a twist. The twist is what? We are considering that the momentum, we are considering or assuming that when the accident is happening or after the accident, both the driver of the car will be not pressing the brakes and not pressing the accelerate button. So that means no external force is given. When the no external force is given, or the no brake or the accelerate button will be pressed by any of the driver of the car, then the momentum, the total momentum of the system remains constant. Yes, but in the time of accident or after the accident, if any of the driver or both the drivers are pressing the brake button or the accelerate button, then they are what? They are giving the external force, right? So they are forcefully trying to reduce the speed by pressing the brake button. That means they are giving external force. Or if they are if they are pressing the accelerate button, that means they are enhancing the force. That means they are giving external force. So then this law will not applicable. This law of conservation of the linear momentum will not be applicable when any external force is given. We will definitely go into the problems, the critical problems, and also, if are you interested, we can show you that formula in a three-dimensional way. Thank you.